Hello, AP Statistics. We are looking at section 2.2 on density curves and normal distributions. So in our section, we are going to be estimating relative locations of median and mean in a density curve, estimate areas of a normal distribution, find the proportion of z-values of a specific interval or z score from a percentile in a standard normal distribution, find the proportion of values in a specified interval or a value that corresponds to a given percentile in any normal distribution, and determine whether a distribution of the data is approximately normal from graphical and numerical evidence. So first, in chapter 1, we talked about graphical and numerical tools for describing distributions, so we'll do one more thing here. We have to make sure that when we're exploring quantitative data, this is one of the first things we talked about, always plot your data. And that would be dot plot, stem plot, or histogram. Number 2, look for overall pattern. Which I guess we could say is our socks here. So that covers the shape, outlier, center, and spread. Then we need to calculate a numerical summary. To describe center and spread. And lastly, sometimes the overall pattern of a large number of observations is so regular that we can describe it with a smooth curve. So we'll summarize that by saying sometimes the overall pattern is so regular we can describe it with a smooth curve, which is what a density curve is. And here we are, a density curve is a curve that is always on or above the horizontal axis and always has an area of exactly 1 underneath it. Because if you think about what you're doing, you're drawing a curve over all of your data values, so you could technically start with a histogram and then just draw a curve over the bars. So that 1, that's representing 100% of your observations. Density curve describes the overall pattern. The area under the curve is the proportion of all observations that fall in that interval. The overall pattern of this histogram of scores of 947 7th graders in Gary, Indiana on the vocabulary part of the Iowa Test of Basic Skills can be described by a smooth curve. So we see the bars, obviously this is a histogram, but because it's so symmetric and consistent that they just drew that red curve over the top of the whole thing. We will be doing more with that in a little bit, but that is just to show what a density curve looks like. Measures of center and spread apply to density curves as well. The median of a density curve is the equal area point, so that divides the area under the curve in half. The mean is the balance point, at which the curve would balance if it was made of a solid material. And remember that the mean is what moves if the density curve is not symmetric, so it would move towards the tail. But the median cuts the areas in half, so exactly 50% of the observations should be on the left and 50% should be on the right. For a symmetric density curve, the mean and the median are actually the same point. The mean of a skewed curve is pulled away from the median in the direction of the long tail. And what that looks like here, your pictures should hopefully be complete on your notes there. The mean and the median should both be this green line in the middle because this is perfectly symmetric. And on this one, the median would be on the left and the mean would be the point that's pulled a little bit to the right by the long tail. So it's idealized, right? Like the one that we just showed with the bars, we kind of cut some of those bars off, but it is what we idealize it to be. We distinguish between the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual observations. The usual notation for the mean of a density curve is mu, which looks like that one typed like that when I write it. And the standard deviation is lowercase sigma, which looks like that written. One particularly important class of density curves are the normal curves. That's what we're going to hear about a lot moving forward here. And normal curves all describe normal distributions. It is important to know all these characteristics about normal distributions. They are symmetric, single-peaked, meaning they only have one tallest point, and they are bell-shaped. Any specific normal curve is completely described by giving its mean and standard deviation. So mean is the center. That's going to be, for a normal curve, always going to be the maximum. And remember, standard deviation is how spread out your data is from the mean. So if on the left one we see that our data is much more spread out, so our standard deviation will be much larger. And on the right, since most of our data is compacted into that tallest peak, then our standard deviation is much smaller. Now, the standard deviation on normal curves happens at the point called an inflection point. If you have taken calculus, you know that means that it's changing from curving down to curving up. So if it doesn't tell you what the standard deviation is, you're trying to find that point at which it stops curving down and starts curving up. So that happens much closer on this one, curving down until a certain point, and that certain point is the standard deviation. A normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by the mean and standard deviation, as we showed on the two graphs on the previous page. The mean is the center. The standard deviation is the distance from the center to the change of curvature points. So this seems to be the summary of what I was just saying. We abbreviate the normal distribution with mean and standard deviation as n. So we put that capital N that tells the viewer or whoever's reading it that this is a normal curve, mu, standard deviation. So that's really all you need to know about a normal distribution. They are good descriptions for some distributions of real data, like the one we just showed with the 847 with the fourth grade students. Anyway, standardized testing tends to follow normal curve. A lot of things follow normal curves, so they're very relevant for us as statistics is going to be talking about real-life situations. Normal distributions are good approximations of the results of many kinds of chance outcomes, and many statistical inference procedures are based on normal distributions, so they are obviously quite important. Although there are many normal curves, they all have some properties in common. There is this special rule, 689599.7 rule, and that states that in a normal distribution with mean, mu, and standard deviation, sigma, 68% of observations fall within one standard deviation of mu. So looking at this curve down here, we have, this is our mean in the middle, 0 telling us that we're 0 sigma, 0 standard deviations away from the mean. So this is 1 standard deviation out in this white area here. This is, I guess we should label that as the 68%. There we go. Approximately 95%. I guess I should label these with percent, sorry. 95% is within 2 standard deviations, and 99.7% of observations are within 3 standard deviations. So anything that is outside of that range, I mean, there is some, like these tiny little tails on the end here, that's a little bit, but it's very unusual for a data value to be that far away from the mean. So using that information about that rule, we have a distribution of heights of young women from 18 to 24, normally distributed between where the mean is 64.5 inches and the standard deviation is 2.5 inches. Sketch a normal density curve. Label the points at 1, 2, and 3 standard deviations from the mean. So normally I am very good at drawing normal density curves. Just a heads up that with this pen that I'm using to record these, it might not look very good, just a warning. That could have been worse, but it wasn't great. So right at this peak here, we have the 64.5, and it says to label 1, 2, and 3 standard deviations away in both directions. So if we know the standard deviation is 2.5, then if I'm going to the right of the mean, I would be adding 2.5 every time. So we'd have 67, 69.5, and 72. And then to the left of the mean, we'd have 62, 59.5, and 57. Okay, what percent of young women have heights greater than 67 inches? So sometimes I like to, like having this first picture down, I can see what the values are at how many standard deviations away. 67 is 1 standard deviation away from the mean. So if I was between 62 and 67, then, it would be 68%. So then if I know how much is in between, let's see if I can do a quick sketch here to visualize this. Keep in mind I'm not trying quite as hard here. Okay, so we have, here's the mean, here's our 67, and if I want to be greater than 67, I know that if I'm between here and here, that this is 68%, which means in the tails of both sides here, it would be 32% of the data split in half, because I know underneath this whole thing is 100%. So if I know between the two dashed lines that I drew that's 68, then here is 16% and here is 16%. So since I just want that upper half, then it is 16. So mathematically we take 100 minus the middle, 68, and divide it by 2 and get that 16%. What percent of women have heights between 62 and 72? So here's where I like to have these sketches. If they're not helpful for you, that's fine. 62 is 1 standard deviation away. 72 is 3 standard deviations away. So I'm going to calculate these in 2 separate pieces here. I want to figure out what these tails are. So to figure out what this lower tail is, I would do 100 minus 68, which would be what is in between 1 standard deviation, but I'm dividing it by 2 since I want just the 1 tail. And over here, it was 99.7 are within 3 standard deviations. So I subtract that and divide by 2 and just get 0.15%. So if I know that 16.5% are in the tails, then in the middle is going to be the 83.5%. 0.85% between 62 and 72. So that's generally how I work on those questions, is I work backwards, like from each piece, each tail, or in between, depending on what's easier. Okay, so now let's look at what this is called the standard normal distribution, and that has some very specific conditions to make it standard. So notice the question we just did prior had a mean of 64.5. The standard normal distribution always has a mean of 0 and a standard deviation of 1. This can also be described as the normal distribution of z-scores, which we touched on very briefly. That standardized variable, again, z-scores, x minus mean over standard deviation, and now that we specifically have names for those things, or variables for those things, we can put it into this formula, and we know that the mean is 0 and standard deviation is 1, as shown in this picture up here. That curvature change happens 1 standard deviation away, so that's at 1 and -1. So what we use for areas for the standard normal distribution is called the standard normal table. That's table A in the back of your book. And you're also going to be given this table when you're doing AP practice. So that is here is what this looks like in the AP practice cheat sheet. This is this whole thing that you get when you take the AP test. But we are specifically going to be looking at these 2 pages today. Table A, it says right on that left side, where some of the z-scores here on the left are negative, and then the second page is where they are positive. So if we want to find the proportion, so the numbers on those tables are always going to give you the values to the left of z. Table entry for each z value is the area under the curve to the left. So suppose we want to find the proportion of observations that are less than 0.81. Here's my picture. So 0.81 is going to be to the right of the peak before the curvature change. So here's 0.81 roughly. We can shade the area to the left because that's what we're trying to find. And then on our table, so here they show exactly what row. Let's look at this all in all. Okay, we're going to look at the positive z values. 0.8 is here, right? You see 0.8. And then across the top, 0.8 and then 1. 0.81. So I come down here, find where those two numbers overlap, and it's 0.7910, which our little excerpt from the table shows here. 0.7910 is the area to the left of 0.81. We will do lots of examples of those, don't worry. We can answer a question about areas in any normal distribution using table A or by technology. So again, I don't have access to a graphing calculator on my computer right here, the one that I'm using. So I'll be sticking to the table for our information. So state the distribution and values of interest, drawing a normal curve and shading with the mean, standard deviation, and boundary value or values are clearly identified. Perform calculations, compute a z-score for each boundary value and use table A, and that's what I'll be doing, showing you. And in class I will go over the technology, the calculator use, but I greatly prefer the table because I don't like relying on technology necessarily. I like to know how to do it by hand, that way I don't make any technological mistakes. But in the calculator, it's under the normal CDF command. So should you want to find that on your own, for now, feel free to do that. So let's do some of these questions. Use Table A in the back of the book to find the proportions of observations from a standard normal distribution that fall in each of the following regions, and sketch. So let's, doesn't have to be huge, just a cute little thing. And we are, here 0, less than 1.39, so that's maybe here. And less than, so that's going to be all of this here. You might want to shade a little more thoroughly. So I'm going to look at my Z table. 1, so this is the positive side, 1.3, going all the way down to 3 row until I get to the 9. I see 9.177. The way we can write this algebraically or mathematically, the P, Z is less than 1.39 equals 0.9177. Okay, next one, greater than negative 2.15. So here's 0, negative 2.15 might be, it doesn't have to be perfect, okay? So if you are like, oh, I don't know if this is at 2.15, you're fine, just label it. And we're greater than, so we're going to do everything over here. Now remember that the table is only giving us values to the left. So if I want greater than, which is to the right, so obviously I shaded to the right since it's greater than that value, I'm going to look at my table at negative 2.15, negative 2.15, and this is going to give me the tiny little area that's to the left. The 0.0158 is the area to the left. Oops, I missed it already. Forgot what it was. 2.15, 0.0158. So if I want to know what's to the right, I need to subtract that 0.0158 from 1. And that's 0.9842. Okay, now we have a problem that's between two Z values. Going to be between negative 0.56, maybe here, and 1.81, which might be here. I want the area between those two. So keeping in mind that the table only gives us areas to the left, I would want to find the area to the left of the bigger number first. So that's going to give me all of the area to the left, and then find the area to the left of the smaller number and subtract them, and that will give me the area between. So to find the area between, I'm going to find the area to the left of 1.81 and subtract off the area to the left of negative 0.56. All right, so 1.81 is 0.9649 right here. And to the left of negative 0.56, I'm going to have to go to the negative page. 56.2877. And that is 0.6772 for the area between. Okay, so now kind of working our way backwards, normal distributions that satisfy the condition that 45% of observations are greater than Z. So this one I know what the area is, but I don't know what the Z is, so we kind of have to work backwards here. If 45% are greater, I know if I was at 0 here, then it would be 50. So I'd have to go a little bit in this direction. Z would have to be positive. They're saying that this shaded region is 0.45, so I need to figure out what this Z is. So what I'm going to look at, since all of those, since all of the numbers on the table specifically give us area to the left, well, I know that the area to the left of whatever the Z is 0.55. So I'm going to find a Z with area to the left closest to 0.55, because it probably is not going to be exactly 0.55. So we're going to have to figure out whichever one is closest. So here all of my areas are less than or equal to 0.5, and I want 0.55. So I'm going to need to go to the second page. 0.55, it looks like the closest is right here. This one is 0.22 away, and this, or 0.0022 away, and this is 0.0017 away. So the closest is 0.13 for the Z-score. That has an area to the left that's closest to 0.55. We're only going to do the 2 decimal places since that's what the table gives us. So I'm sure we can get a more accurate Z-score, but this is the one that, based on the table, the one that's closest is 0.13. So that last example that we just did was kind of the working backwards situation. Sometimes we may want to find and observe value that corresponds to a percentile, so that's what we just did, that last example. So state the distribution and values of interest, drawing a picture, which I think really helps. Perform calculations, show your work, do one of the following things, use the table, which is what I'm going to stick with, and we're going to do what's called unstandardize to transform back to the original distribution if it wasn't just on the standard normal distribution, or use the inverse normal command and label each of the inputs. So let's do an example here where we're talking about high levels of cholesterol. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, where the mean is 170 and standard deviation is 30. Cholesterol levels above 240 may require medical attention. What percent of 14-year-old boys have more than 240 milligrams per deciliter of cholesterol? So we need to, I guess we could draw a quick picture here. The mean is 170, and we're way over here at 240. So if I'm going to calculate this with a Z-score, I need to turn this into a Z-score, which is x minus mu over sigma. Z-score at 2 decimals is 2.33, and I want to be greater than 2.33. So what I'm going to do on the table is do 1 minus what I find to the left of 2.33. So looking at our table, the positive value is 2.33. 0.9901 is our Z, or our area to the left. So 0.0099 is the percent of boys that are above that, about 1% or so. People with cholesterol between, that's going to be too late, between 200 and 240 are at risk for heart disease. What percent of 14-year-old boys have cholesterol between 200 and, this should say, 240? 400 would be dead. So here's our 170, 200 would be here, and 240. So remember, when we're calculating area between, probability of, let's just say we'll do x first, between 200 and 240. We have to turn those both into z's. 200 minus 170 over 30, which is going to turn them into z's. And those z's are 1, and we already did the 2.33. So I'm going to find the probability less than 2.33 and subtract the probability of z less than 1. If we remember how to, we do the area of the bigger one minus the area of the smaller one. So let's see, 2.33 we just found was 0.9901. And less than 1, 0.8413. Which is 0.1488. So almost 15% of boys are at risk for heart disease. What is the first quartile? So remember that quartiles correspond to cutting our data into quarters. So if we're looking at in terms of z's, we're going to work backwards here. First quartile, whatever z value this is, needs to correspond to 25% of the data being to the left. So what I need to do first is look in the z table and find inside the areas and work outside to figure out what z value corresponds to 25% being to the left. So looking through here for the closest one, looks like it's right here, which is 0.67, negative 0.67. But I don't want to know what the z is. I want to know what the cholesterol is. So keep in mind that our formula for z is here. Z equals x minus mean over sigma. I just have to solve this for x. So multiply the z-score by the mean and add, or by the standard deviation and add the mean. We're going to get 168 milligrams per deciliter. All right. Normal distributions provide some good models for some distributions of real data. Many statistical inference procedures are based on the assumption that the population is approximately normally distributed. As we get further along, you're going to see that a lot of our inference is going to say assuming normal distribution. So if we don't have that or don't know if it is, we're in trouble. So we use something called a normal probability plot. And it provides a good assessment on whether a data set is normal or not. If the points on a normal probability plot lie close to a straight line, then it indicates that the data are normal. Systematic deviations from a straight line indicate non-normal distribution, and outliers look like they are far away from the overall pattern. So this is going to be a little tricky here because I don't have access to the calculator that we need. I am going to just give you the steps that you will need to follow on your TI-84 Plus. So please, if you need more assistance with this, please come see me about it. I have no problem helping you, but I don't have access to recording with a calculator here. Okay, so since we need the data to be in order to assess normality, we have arranged unemployment rates from all 50 states from lowest to highest. So the smallest is 4.1, the largest is 14.7. So what we're going to do first is plot all that data in stat edit, right? That's going to be where we have our list, plot it all into L1. After all of our data is inserted, then we go to stat plot, And we want the last graph type. Which looks like that. When you choose your options, your data axis should be X. And then we hit zoom 9, which fits to our statistics. Make sure that our stat plot is on, by the way, in order to do this. And we look for linearity in the dots. I'm sorry I can't do more with that. I just don't have access to that right now. Okay, so in this section we looked at relative locations on a density curve, estimated areas on a normal distribution, finding proportions of z-values for specified interval, find the proportion of values of a specified interval or a value that corresponds to a given percentile, and determined whether a distribution was normal based on the normal probability plot. So that covers our section 2.2, and we are completely done with chapter 2. That was a quick one. Have a great day. Talk to you again soon.